This is the second last video in Work and Energy. In this video, we'll be looking at one of the fundamental universal laws of physics, which is the conservation of energy. And this is not a law that the universe can disobey and live. So we saw that if a conservative force acts upon an isolated system, then the mechanical energy of that system is conserved. So that is, with a conservative force, at any point in time, the mechanical energy of that system must be the same. So when a non-conservative force acts, the initial mechanical energy of that system is not the same as the final mechanical energy. So mechanical energy is either lost or gained from the system. So if the system is isolated, we cannot gain or lose energy from the environment. So something is happening to the mechanical energy. And in order to look at what that is, we need to look at the law of conservation of energy. So this is a physical law, that must be obeyed. And it states that energy cannot be created or destroyed, but it can be transformed from one form to another. This law followed from the law of conservation of mass, and it was first stated in its present form by Julius Robert Meyer, who was a German scientist, in 1841. So how do we know this law is true? Well, the mathematical proof for this law was not made until the early 1900s by a woman called Emmy Noether, who was a sincerely brilliant theoretical mathematician. So around the time when Einstein was publishing his theories on relativity, and it is also the time where women were only just being allowed to vote in some countries. So this woman was publishing mathematical discoveries that are as important in their way as Einstein's or Darwin. She was a fantastic teacher and a mentor, and a very large percentage of her students turned out incredibly important works that also changed the face of mathematics. So she was indirectly responsible for all those works, and she was also directly responsible for many, many more discoveries than are attributed to her. So I've put links in the resources page about these scientists, as I think they're really well worth a read, just for interest's sake. So what Emmy Noether actually did was to prove that if time is invariant, then energy must be conserved. Time invariance refers to the idea that what we do is independent of the point in time that we do it. So for example, if we perform an experiment in the lab, and if the experimental conditions are exactly the same, then we will get the same result from that experiment, whether we perform it today, tomorrow, last week, or some 50,000 years in the future. The point in time that we perform it doesn't affect the experiment, it doesn't matter. So time is not a variable that affects the experiment. So if we think about that, if we perform an experiment that requires a certain amount of energy and it releases a certain amount of energy, then that amount of energy must be available whenever it is that we choose to perform the experiment. And we can make our imaginary experiment as big or as small as we like. So it can use as much or as little energy as we like. So the total energy available at every point in time must be the same. And that's the conservation of energy. So it's not possible for us to entirely prove this. We'd have to be able to live forever. But every experiment that has ever been done has achieved the same result, which is that energy is always conserved. So if we have a system where a non-conservative force is acting, so mechanical energy is lost from the system, but that system is isolated from the environment, what's happening to the energy? So if we have an apple moving with some kinetic energy across the floor, over time we see that the apple slows down and the initial kinetic energy is reduced. Some of that energy is converted to heat, and some is converted to other types of energy, for example sound. So in order to describe the total energy of our system, we now need to include two more terms. So we have the mechanical energy, kinetic and potential, and we need to include our thermal energy or our heat energy, and the other types of energy which are written with a subscript, etc. But which is more often written as the internal energies. In an isolated system, that system cannot interact with the environment around it. So the total energy of that system cannot change. It has nowhere to come from and it has nowhere to go. But what it can do is it can take different forms, as long as the sum of those forms is the same at any point in time. So if we consider a system in which we have an ice cube and a certain amount of heat, our total energy in the system is initially the heat energy or the thermal energy plus the potential energy of the atoms in the ice cube. The physical process that occurs is that the atoms in the ice cube absorb the heat, and they convert this heat into kinetic energy. So the atoms in the ice cube start to vibrate. And once they have absorbed enough heat, they have enough kinetic energy and they're vibrating fast enough that they no longer hold a solid shape and they become water. So in this case, our thermal and potential energy has been converted into kinetic energy of the atoms. As the remainder of the heat is absorbed by the atoms in the water, the same thing happens. They convert that thermal energy into kinetic energy and they start to vibrate even faster. They start to vibrate fast enough that they tear themselves apart and they become a vapor. And so at this point, all of the initial thermal and potential energy has been converted into kinetic energy. But because the system is isolated, the total energy at each point in time is the same. If the system is not isolated, then it can interact with its environment. And the conservation of energy applies then by saying that the total energy of that system can only change by the amount transferred to or from the environment. So again, in the case of our ice cube, this time we'll take our initial system as only containing the ice cube. So the initial energy of the system is just the potential energy of our atoms. If we then let heat flow into our system, our ice becomes water, and the total potential energy is now converted into potential plus kinetic energy. More importantly, the total energy of the system is now equal to that initial energy plus the change in thermal energy. In the opposite case where energy is lost from the system, so say our water has now been converted into water vapor and some of that vapor has escaped from our system, we've lost the kinetic energy associated with that vapor. And the final energy in the system then is equal to the total kinetic energy of the system minus that kinetic energy that was lost. And as an opposite example, if we say that some of our water vapor escapes from the system, then we lose the kinetic energy that's associated with that water vapor. So the conservation of energy means that we can always account for all the energy in our system. So in summary, the terms conservative and non-conservative forces relate only to the mechanical energy of the system and whether or not that mechanical energy is conserved. The law of conservation of energy relates to the total energy of a system, which is that mechanical energy plus the thermal energy plus any other form of energy. And it states that that total energy must always be conserved.